Okay, guys, so today we're going to learn something quite different. It's called induction. It's not too difficult and it's quite cool. It's basically one of the ways we prove things in maths. We don't do a lot of proofs in maths. The only way we do it, the only time we do it in high school is with geometry, which I personally really dislike. But this is much better and it is awesome. It really is, okay? So if you remember last year when we did Riemann sums, okay, there were things like sigma I goes from 1 to n, okay, equal to n times n plus 1 over 2. So if I do 1 plus 2 plus 3 plus 4, up to a certain number, let's say n could be 1,000. If you want to know that sum, all you got to do is that last number, okay? If let's say you went up to 100, okay? So if you want to know what is 1 plus 2 plus 3 plus 4, all the way to 100, you just do 100 times 101 divided by 2. Okay? Maybe it rings a bell, but yeah. It's a rule, yeah. It's an equation that you actually get given. You're given that in the exams, and you use it. We use that in Riemann sum. Okay. What we're going to do now, we're going to prove it. Okay, and in fact, we're going to use that to prove a whole bunch of other things we use in Riemann sum. And just think about it. You know, how cool is it to actually that we can actually prove it? You know. I mean, we can try it out. We can try it to 100, 1 plus 2, put in the calculator, 1 all the way to 100, and then put 100 times 101 divided by 2, and it works, great. But how do we know that it's going to be right if we go up to 1,000? How can mathematicians actually prove something? That's only in maths. You won't have it in physics, in other sciences. Okay? In science, scientific theories, you can only disprove a theory. Maths is the only thing that you can actually prove it. And if you think about it, that's why we still study things that the Greeks discovered 2,000 years ago. Because you can't disprove it. They actually prove it. So how are we going to do it? We're going to do it with 3 steps. Okay? The first one is check for n equal 1. Okay? So we're going to try for n equal 1. Okay? What do I mean check for n equal 1? Let's go with just 1. Okay? So if n is equal 1, I have 1 plus 1. Is there any more numbers? No, it's the last number. Okay? So our last number is going to be 1. So it's just 1. Okay. Let's see if it works with this thing. Okay? If that formula is correct, then 1 must be equal to 1 times, what is n? If n is equal to 1, what is n plus 1? 2. Okay? I'll write it like this. 1 plus 1 divided by 2. Which is 1 times 2 divided by 2 equal 1. Boom. Got it. So it works. So that's the first step. Okay. Now comes the second step. Assume is with the E, right? It's okay for n equal k. Okay? So we're going to think about a certain number, k, which could be any number. It could be 3 or 5 or 17 or 500,000. And we're just going to assume that it's correct. You'll see why we're doing it. Okay? So we're going to assume. We're going to say that 1 plus 2, this is the first step, the second step. 1 plus 2 plus 3 plus all the way to k. That is going to be equal to what? So in other words, instead of n, you write k. K times k plus 1 divided by 2. Okay, we are going to assume that. Okay, I'm emphasizing that assume. Okay, right. What we need to do now is prove that if this condition is right, still okay for n equal k plus 1. Do you guys do like coding, IT?
Yes.
Yeah? So I don't do the language now, but when I was younger than you, I learned basic. And I'm sure it's still in the codes, it's still like, if this, do that, blah, blah, blah. And then some point you will say, go to that first line. loops. No, you've got this idea of loops. What we're doing is a loop here. Okay, let me try and explain. So we got it for 1, that's fine. Now let's say it's true for n equal k. Okay, let's say k is equal 3. So let's say it's correct for 3. Okay, now if we manage to prove step 3, and we assume that it's correct for 3, what about 4? Will 4 work? Well, okay, I started in the wrong place, sorry. Because we didn't check for 3, didn't we? It was just an assumption. But what did we do check for?
For 1.
For 1. So if it is true for 1, so it's absolutely true for 1. Now here we assume that if it's true for, let's say 1, here we prove that it will be true for
K plus 1, because you assume
which
it's
2?
true for k.
Okay? So, but I've checked for 1. I definitely checked for 1. So first of all, I checked for 1. Now these two conditions together, if it's true for 1, then it must be also equal to 2. Right? If I proved it. I haven't proved it yet, but I need to prove it. Okay. Okay, I will come back to that in a second. Let's actually just do it, and then I'll come back to that point, okay? All right, and how do we actually do it? Okay, so we assume that this is correct, okay? Now we need to prove formula is okay, is right for n equal k plus 1 to the next one, okay? So let's try and do it, okay? So I'm going to do now 1 plus 2 plus blah, 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 plus k, and I'm going to check for, basically what I'm going to do, I'm going to add k plus 1. I'm going to add that now. And see if it will be right for, to the right side will be fine as well. Now, I'm assuming that one. I'm going to put that in blue. I've assumed that. Okay? So, therefore, what I've done, by adding k plus 1 to that side, I must add k plus 1 to the other side. Is that right? Okay? So, I'm going to write k plus 1, 5 by 2 plus k plus 1. Okay? Now, I'm going to rewrite this one. 1 plus, I'm going to actually write the whole thing, plus k, or not the whole thing, I'll just take just these 1, I didn't do anything, okay? And now what do you reckon we can do here? Pull them up, okay? So we're going to put 2, and let's open it up at the same time. So what shall I write? K times k, it's not, there's no 4.
K.
So k squared plus k plus 1.
Isn't plus 2k plus 2?
Yes, you're absolutely right. And I would have get stuck if you didn't tell me that. So, because I multiplied this whole thing, lifting up, I have to multiply it by 2. Absolutely right, okay? So now I'm going to write this thing, I'm not going to repeat it. It's the same thing, okay? Okay? And let's try and get some factorization going on here. So I'll write that again as k squared plus 3k plus 2. How's your trinomials these days? Okay, k squared plus 3k plus 2.
Yeah, k plus 2 is k plus 1.
Aha. Okay. Now I will just say that that's it, you proved it. Well done. Why? Okay. Let's write maybe what I've written here. 1 plus 2 plus plus k plus 1. This is the sum of the first k1 terms. Right? This was the sum of the first k term. And with that k plus 1 is the first of the k1 terms. Okay? What do I have here? This is basic. Look, let's just have a look here. When n equal to k, okay, when n equal to k, I know that that sum of these k terms will be the last term, k, time the one after that one, which doesn't even appear here.
Now you're just passing 2 because there's 2 terms.
Exactly. Now I've got, okay, now I've got n equal k plus 1. The last term is k plus 1. And what did I just prove here? That also is going to be the last term, k plus 1. I should probably swap them around. put the smallest one first. So k plus 1 plus k plus 2. Obviously, that's the same. So that's the last term here. That's the last term here. And then that's the one next. So what I've done here, I proved for n equal k plus 1. Okay? I'm going to just repeat it and then don't worry, off the record, we're going to solve any problems. Okay? So what I've done here, first bit, I put n equal 1. I checked for n equal 1. And it worked. Now I assume for n equal k, where k can be any number. I just assumed it. Now I use this assumption, okay? I assume that it's correct for n equal k to prove that it's also correct for n equal k plus 1. Okay? I assume that is correct, okay, for n equal k, and I prove that it's also true for k, n equal k plus 1. Now, why does that work? Why does that work? Because I've already proved that it's true for 1. But if it's true for 1, in 2 and 3, I proved it's also true for 2. Because if it's true for n equal k, it's now proved that it's true for nk plus 1. So if it's true for 1, it's also true for 1 plus 1, which is 2. But if it's true for 2, it's also going to be true for
2 plus 1.
2 plus 1, which is 3. And it's also going to be true for 4, and so on and so on. So you've got a loop, a recurring loop, a recursive loop in your code, and you prove that it's true for all numbers. Okay? I'll pause here and see what you've got to say. Okay, so I want to do 2 more examples, but before, I didn't use the word induction. What does induction mean? Have you heard of induction before? Yeah, it's about, well, it's actually, it's a proof based on an assumption. So it's like, if let's say, how can I tell that the sun's going to rise tomorrow?
Rose yesterday.
And the day before, and the day before, and the day. So I have an experience of many, many days where I saw the sun rising. So I'm saying, okay, if by experience, it probably will rise tomorrow as well. So that's an induction, but actually the induction we're doing is stronger. Because the induction we do about the sun is just by experience. Okay? Here actually is deeper things. You know, maths is a deep thing. Okay? So Olivia spoke about dominoes. And it's a little bit like dominoes. Okay? Let's say I've got a whole bunch of pens. And I want to prove something about them. I don't know what they're nice, they're pretty, they're whatever. Okay? What I've got to do is, and I've got millions of them in a row or in a column, whatever. Now, what I've got to do is that if it's true for one pen, it will be true for the one next to it. So if I manage to prove that this one has this quality, let's say it's good writing on the board, then if I manage to prove that the one next to it must also have it, somehow I prove it. That's the hard bit. That's what we're going to do. And then I just need to do one more thing. I need to prove that one of these pens have that quality. So let's say I prove that if the neighboring pen has that property, the other pen will have it. And then I prove that the blue one has that property. Well, if the blue one has that property, definitely the black has the property, and therefore the green has the property, and the next. It's kind of like domino, okay? I just put them in a way that if one is correct, the one next to it is correct. The one number after that will be correct. And then I just need to prove one of them is right, and then they will fall. Okay? So don't think about it too much if it's confusing. Example is the way. So I've got this number, 9 to the power of n plus 3. I want to prove that it's divisible by 4 for any natural n. Now, this is what we call pure maths, number theory. We don't do a lot of it in high school. And also in university, I didn't do it. Okay? I did a lot of maths. It was all applied maths or physics. So this is quite crazy. How can you prove that 9 to the power of n plus 3 is always going to be divisible by 4? Okay? And you know what a natural number? What's the natural numbers? Give me 1, 2. It's what I call hide and seek numbers, right? 1, 2, 3. You don't have 0. You don't have -5. You definitely don't have square root there. 1, 2, 3, and so on. Okay, so we're going to start with steps. What's the first step? Check for
1.
For 1. So we're going to just substitute. That's the easy step. So even if you get lost in the exam, you haven't got, I can't remember what is induction. Just check for n equal 1. You'll get a couple of marks there, okay? So for n equal 1, I got to write 9 power 1 plus 3. How much is 9 power 1 plus 3? There you go. 12. That's it. You don't need to calculate. Okay, 9 power 1 is 9. 9 plus 3 is 12. Can I divide 12 by 4? Yes. So, check. We got that. Can be divided by 4. Right, next step. Assume. So we assume. Okay? Assume is true, is okay, or it's true. Not okay, it's true. Be a bit formal. Okay? It's true for n equal k. So we are making up equation. We say, okay, so instead of n, we're going to write k. So n power k plus 3. Okay, now here comes the tricky bit. Okay? Here comes where you have to actually think. How can I say that this number it can be divided by k, by 4? How do I write it? Like that's equal to x or y or z? Okay, let's think about all the factors or all the multiples of 4. It's going to be 4, 16.
4, 12, and
That's it. But let's not leave n because we've got already n. Okay, 4 times. Okay, x is fine, but x is like something that we usually try and find out. Let's call it, I don't know, r or whatever. Okay, s. You can use x, that's fine. So a number that is a multiple of r, or multiple of 4, in other words, this must be a multiple of 4. If we can divide by 4, if I say I can divide that by 4, that's the same thing as saying that it's a multiple of 4, right? So in other words, it's going to be 4 times r, where r is, what does that mean?
integer.
It's an integer. R belongs to an integer. Okay? Right? Okay, now I need to prove. What do I need to prove?
Prove that it works for n equals to 1.
So it's true. We need to prove it is true for n equal k plus 1. Okay? So in this case, in the first case, I've added plus k plus 1. Now, I'm going to start slightly different. So I know this is true. I'm going to write that, circle it, because I will use it later on. But now I'm going to try and find out, okay, 9k plus 1 plus 3. And I'll try and find out what this business is. Okay? Okay. Now, I want to show that this thing, I'm going to rub this in a minute, but I want to show that this thing is also 4 times another number. It's not going to be r because they're not equal. These two things are not equal.
Yeah.
So it's going to be 4 times s, another integer. Okay? But I need to prove it, so I'm not going to write it. Now, the way to do it, you always want to make this side look like this side, maybe plus something. So I'm going to leave the 3. If I want to write 9 power k, what must I do? What must I add to that 9? Because it originally it's plus 9? Time.
I mean, yeah, sorry.
Time. Okay?
Figuring that.
Yeah? So 9 power 1 times 9 power k is 9k power 1. Okay? Now, what do you feel like doing now?
Given that there's so many 9s and 3s, just do that.
Okay, so 3. What will you do with the 9 and the 3?
3's about.
Because I want to make it. I don't know if that's the right thing. I feel like I want to get this, a factor of 3, but I don't know if that's going to help me. So let me just check. Yeah, I think it does help me. No, actually, no. That wouldn't have helped. That wouldn't have helped. No. Okay, so this is. Well, but hang on. This is not an equation. This is where things are a little bit difficult. I mean, it's not that equal. Well, obviously that equal to that, but that's not going to help me find. I'm just simplifying.
They're underneath each other. The equal times.
Yeah, I mean, if I had. Yeah, if it's under each other, under each other, yes. I remember we had a chat about that once. Okay, so Okay, this is a tricky one. This is actually example is a bit more tricky. Check this out. Because I have 9 to the power of k, okay? What is 9 to the power of k according to this equation? 4r. Just 4r? 9 to the power of k plus 3 is 4r. Minus 3. Okay? Right? Now, that baby here, I want to put in there. Okay? I think it would have worked if I just get a factor out. I'll maybe check it later. But now I'm going to write 9, and instead of 9 to the power of k, I'm going to write 4r minus 3, and then at the end plus 3. Okay? Let's see what happens now. Okay? Equal below. Okay? What is 9 times 4r? 6r minus 9 times 3, 27 plus 3 equal below 36r minus 24. Is that right? Think so? Okay. Now, I guess now we can take a factor out. Okay. So what factor can I take out? 36 and 24? 4, which is perfect. Okay. So 4 times, what do I have here? 9r minus 6. Is that right? Now here I'm claiming that we managed to prove it. But the question is why? What did I prove? Okay, let's think, what did I want to prove? So I wrote it here, which is good. Need to prove that this formula is true, or what is the formula? That n power n plus 9 power n plus 3 is divisible by 4. 4 n equal k plus 1. I need to prove that it's divisible by 4. Okay? Now, where did I start? With substituting n equal k plus 1. 9 to the power of k plus 1 plus 3. That's where I started. So I just substituted instead of n, I put n equal k plus 1. N equal k plus 1. Now, what did I show that this thing is equal to? 4 times 9r minus 6. 9r minus 6. 4. Okay, so we proved that this thing is a multiple of 4. Because obviously r is an integer. So if r is an integer, I don't know what integer is, 7, 17,000, whatever, then 9r minus 6 is also an integer. And integer times 4 obviously is divisible by 4. So n equal k plus 1 is divisible by 4. Okay, I don't know why I said it's easy. Actually, it is difficult. When my mind, when I thought about it, it's easy. But yeah, now I can see when you actually try it, it is quite difficult. Okay, so I'll just pause here and we'll do one more example. Okay, so we made a little decision because I can see, the guys here, struggling a little bit. We decided to pause here. I solved you 2 examples. On Thursday, instead of doing the complex numbers, we'll carry on. I've got 2 more examples. And so we're all going to be together on Thursday, and hopefully by that time you'll figure it out. So at this point, I don't want you to do any exercise regarding to that. I need one more lesson to kind of get it right. What I would rather you do now is look at your complex numbers, the chapter from grade 10. Hopefully you got the photocopies for me. And I want you to start reading that. Okay, I'm not going to do complex numbers on Thursday. I'm going to do them next week. So we'll have one more lesson on induction. And next we're going to go complex numbers and it will be fast. So please, for now, start looking at the notes for complex numbers. See you on Thursday.